Hello students, this is Mr. Allen. Today we're going to look at section 6.2, which is on volumes, the disk method, and the washer method. I am actually skipping over section 6.1, which is areas between curves. I just feel like that's something that we can kind of move on beyond. I hope you feel the same. So let's get to it because there's three big ideas we need to talk about here. We need to figure out how to find a volume of a solid of revolution using the disk method. We need to use the washer method to find the volume of a solid that way. And then finally, we want to look at known cross sections, using known cross sections to find volumes. So if we have a region in a plane that is revolved about a line, the resulting solid is a solid of revolution. And the line is called the axis of revolution. The simplest such solid is a right cylindrical cylinder or a disk, which is formed by revolving a rectangle around the axis adjacent to a side of a rectangle, so as you can see in the photo here. The volume of such a disk is related to pi r squared, but we also have to multiply pi r squared as the area formula for a circle, but now we've got a circle that has some width. So it's going to be pi big R squared times the width of the disk, W. To see how to use the volume of a disk to find the volume of a generalized solid revolution, consider the following. So here we have some function. It's a curve. And then we've got the small little rectangle here drawn in our first picture here. And that rectangle has a height of R. That's the radius, and a width of dx, so that's like your width. So what we could do then is we could think of that if we were to revolve this entire solid. Now we're looking at the middle picture. It's going to give us, it almost kind of looks like a Hershey's Kisses shape. We could think of that, instead of thinking of that as a nice smooth curve, we could think of that as a bunch of disks that we're using to approximate that. And of course, if we increase the number of disks, we're going to get a better approximation. So this gives us our formulas for today, for at least for the disk method. So the disk method basically, and I'm just going to focus on the horizontal one for right now. The formula is volume equals pi integral from A to B of big R of x quantity squared dx. Of course, if we were doing this with respect to the y axis, everything's going to be in terms of y. I expect you'd be able to do both. So let's look at an example using the disk method. Find the volume of a solid by revolving a region bounded by the graph of y equals the square root of sine x and the x-axis from 0 to pi about the x-axis. So graphically, if we look at this, this is what we're going to have. Here's our 2D shape. So that's the sine curve. That's actually, I'm sorry, that's the square root of the sine curve from 0 to pi, which is what we're looking at. And now we're going to rotate this, revolve this around the x-axis. That's going to give us this solid here. And in this case, the radius, the big R, is simply our function value, which is the square root of sine x. And then delta x, of course, is going to be the width of each of those rectangles that you can see in the first picture. So to find the volume of this solid of revolution, we're just going to use our formula. Since this is with respect to the x-axis, it's going to be pi integral from A to B of big R of x squared dx. In this case, our R of x is the square root of sine x, so we just plug that in. We're going from 0 to pi, and now we're just going to go ahead and calculate this out. When you square the square root of sine x, you get sine x. The antiderivative of sine x is negative cosine x, evaluated from 0 to pi, and we get the final answer here of 2 pi. So the volume of that solid that's generated by the square root of sine x from 0 to pi turns out to be exactly 2 pi units in volume. Now the washer method is, we're basically going to use what we just did with the disk method. It's just now with the washer method, now we've got this inner area is being, or inner volume is being subtracted away. The disk method can be extended to cover solids or revolutions with holes by replacing the representative disk with a representative washer. So if you think this is now a washer, it's got a hole in the middle, so that's why we call it the washer method. And in this case here, we're going to use our same formula here, which is pi big R squared W, but what we're going to do is we're going to minus little r squared, because what we're doing is we're minusing out that inner radius, if you will, that smaller internal disk. To see how this can be used conceptually, we look at this curve here. We have a function here. This is the big R of x. And then we have another function in here. Let's say this is little r of x. If we were to revolve that around the x-axis, we would get something that looks like what we have there on the right. So as you can see, it's actually got some more thickness here in the middle and less thickness on the ends. It almost looks like kind of like a dog collar. So here's our general formula for the Washer method. The Washer method, and this with respect to the x-axis, is pi integral from a to b of big R squared minus little r squared dx. Let's look at an example of the Washer method. So this is actually very similar to the previous example, except now I've actually got, it seems like this may be disk method because there's no missing part in the middle at 0, but clearly there's going to be missing areas as we move out away from 0. Okay, so let me clear all that stuff off. Good. All right, so we are trying to find the volume of this solid that's being revolved. Our big R is the square root of x. Our little r is going to be x squared. So you can, this is something that you might want to do if you get confused on these, is to simply just draw that 2D picture to give you some idea of what we're dealing with. And it's easier to kind of draw your representative rectangles. In fact, sometimes you'll see me in class, I'll draw my big R from all the way from the top function to the bottom function, and then my little r is from the x-axis to the lower function. I do top minus bottom when we're talking about the x-axis. Okay, so let's keep moving. So we got big R is the square root of x, that's our outer radius. Of course, little r, our inner radius, is going to be x squared. Now we just plug it into our formula. I should note that we're integrating from 0 to 1. So those are going to be our limits of integration. Okay, please don't forget you've got to square each of these. And when we clean this up, so the square root of x squared, that's just going to be x. And x squared squared, that's going to be x squared. The antiderivatives are going to be x squared over 2 and x to the 5th over 5. We're going to integrate from 0 to 1. And we get a nice answer of 3 pi over 10. 3 pi over 10. So the volume of this shape is exactly 3 pi over 10 units. All right, so far the axis of revolution has been horizontal, and you've had to integrate with respect to x. In this example 4, this is actually, I'm sorry, not example 4, this is going to be example 3. We're going to do a vertical example before we do our final example, which is going to be on the known cross sections. So what I've got here is I've got several curves. So I've got y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. So if I graphed all of these on the 2D graph, this is the 2D graph, we get something like this. Now we're going to revolve this around the y-axis, so that's going to produce this solid of revolution here. So what we're going to do on this problem is, first of all, I'm doing this example because we're going to do it with respect to the y-axis. And second of all, you're actually going to have to do disks and washers to get your answer here. So the first thing we need to be aware of is, since let's just focus on this equation. That is a function written in terms of x, the variable x. We need to convert that to a function in terms of y. So you just solve for x and you'll get r, or if you want to think about it as x, x equals the square root of y minus 1. We're going to call that r, and that's going to be our little r when we do just this portion. That's our little r, that's our inner radius, because remember, now we're doing it with respect to the y-axis. Our big R is going to be this function right here, which is just going to be x equals 1. I'm going to erase all this stuff so you can see this. And then, of course, down here, this bottom piece is going to be a piece of cake because it's just going to be a cylinder. It's going to be a disk method. Big R is going to be 1, and little r is going to be 0. So let's go ahead and work this out now. So we're doing the following, and I'm not going to read all of this, but basically it's all the stuff that I've just said. So we've got two parts we've got to deal with, and we're going with respect to the y-axis. So we're going to go from 0 to 1. That our little r is going to be 0, and then once we get up from 1 to 2, it's going to be the square root of y minus 1. Our big R stays the same throughout the entire picture. So now we're going to plug this in. This here is that bottom half of that solid. So we're integrating from, it's pi times the integral from 0 to 1. The outer radius, or big R, is 1. The inner radius is 0. So this is our first piece. The second piece, this is our upper part of that shape. Now our outer radius is still 1, but now our inner radius is this square root of y minus 1. So now we're just going to go ahead and clean this up and integrate. So the first thing basically becomes just 1. The second thing, after you clean that square and subtract, you get 2 minus y. So this actually turns out to be a fairly straightforward integral. The antiderivative of 1 is y. The antiderivative of 2 minus y is 2y minus y squared over 2. Now we're just going to start plugging in values. Of course, the first one is just 1, and the second one we got 4 minus 2 minus, it'd be the quantity 2 minus 1/2, but that just becomes negative 2 plus 1/2, and we get the final answer of 3 pi over 2. So that would be the exact volume of that solid. Exact volume of that solid. Note that this first integral was from 0 to 1 dy, represents the volume of a right circular cylinder with a radius of 1 and a height of 1. We could have done that without calculus, right? So what is the volume of a cylinder? Just to remind you, I'll call it V sub s. That is pi r squared h. Well, in this case, the radius was 1, the height is 1, so that volume would have just been pi. So that's where the pi comes from. Okay, with the DISC method, you can find the volume of solids with circular cross sections whose area is A equals pi big R squared. This method can be generalized to solids of any shape as long as you know the formula for the area of the arbitrary cross section. Some common cross sections are squares, rectangles, semicircles, and trapezoids. So that leads us to our final discussion, which is the volume of a known cross section method. So here's what we're dealing with, and let's focus on this guy here. So this is with respect to the x-axis. So the cross sections are perpendicular to the x-axis. Note that this is the x-axis here. Again, I'm going to clear all this off so you can see. So notice that the cross sections are perpendicular to the x-axis. So here would be the formula in that case. It'd be volume equals integral from a to b of the a of x dx. The a of x is the shape of whatever that cross section is. So that could be a circle, a square, a rectangle, a triangle, whatever. If we're doing with respect to the y-axis, it's the same thing. It's just in terms of y. Okay, so let's look at our final example. Here's example 4, a triangular cross section. So it says find the volume of a solid. The base of the solid is bounded by the following regions. F of x equals 1 minus x squared, and g of x equals negative 1 plus x, I'm sorry, not x squared, x over 2. So we've got these two curves graphed here. Notice that this is simply just an xy plane, okay? So that's a triangular base. Now, the shape that we're going to do, the cross sections, are going to be perpendicular to the x-axis, and they're going to be equilateral triangles. Okay, so this one's a little bit harder because you kind of have to know the formula for the area of equilateral triangle, which I'm going to give you here in just a second. But if we look back at this picture on the left, you have to be able to kind of visualize how these triangles are going to look as we move along the x-axis. So you can see how those triangles are, in this case, we go from 0 to 2, they're getting smaller. And I should note that we're going over here to 2. So the base area of each triangular cross section is as follows. So if you take the, let me go back to this. If you take this top curve minus the bottom curve, in fact, let me do that right now. That's going to be 1 minus x over 2 minus 1 plus x over 2. And don't forget, minus a negative is plus a positive. So this is going to be plus, plus, and then negative. So that's going to be 1 plus 1, and then x over 2, I'm sorry, negative x over 2 plus another negative x over 2. So hopefully you can see that that's going to be 2 minus x. So I did top minus bottom. Now here's that formula for the area of an equilateral triangle. I claim that You do not need to know that, even though we can easily derive that, but that's what it is. So if I have an equilateral triangle like this and the base is 5, then the volume, or I'm sorry, then the area can be found by radical 3 over 4 times 25 would be the answer to that. So our area function in this case, and this is the key for this problem because our formula says that the volume is equal to the integral from a to b of our area function dx. So this is important, and here it is. It is this formula, the area of an equilateral triangle, with the base length thrown in there. So 2 minus x goes in for the base. Now we can go ahead and work this out. We're going from 0 to 2. So we're going to get the integral, definite integral from 0 to 2 of radical 3 over 4 times the quantity 2 minus x squared dx. Now we get the antiderivative of 2 minus x squared. And we're just going to use our generalized power rule. Please note that negative came there. And the reason that negative came there is because we're going to have to do little u sub there. And we get a final answer of 2 radical 3 over 3. That is the exact volume for that previous problem that we were looking at. And that's going to call it an end. Thank you for your time.